everybody for joining us. I am honored to introduce Diane Fairclough, and she is a veteran of the PCRC. She was there from the very beginning, was the former director of the Data Informatics and Statistics Core. She is incredibly well-versed in statistical analyses, and one of her favorite topics is missing data. And so we heard her talk in the last face-to-face investigator meeting about the importance of it. We thought it would be a great topic for our investigators to learn more about. And so without further ado, I would like Diane to teach us a lot about strategies for handling missing data in palliative care research. Thank you, Diane.
Thank you. So just before we start, the first screen shows what your screen looks like a little bit. So if you have a question, do enter it into the chat box and send it to Sarah, because she's going to be the one that's going to mute and unmute your particular line when we come to questions. And we'll probably do all the questions at the end. The thing is it will be very helpful if you mute your telephone lines so that barking dogs and other things over pages don't interrupt us. So thank you for that. Okay, I'm going to go. Just to, conflict of interest, I do have a book, and I will refer to it. I probably only make about $2 a book, so if you buy it, it's not going to be much profit for me. But it really goes through many of these issues and actually has SAS and SPS and R code for many of these analyses, so it's really it's meant to be very practical. So here's my outline, and so I'm going to first just talk about what the problem is and a little bit of definitions about types of missing data. I'm going to really go into some prevention and mitigation strategies, talk about possible analyses, and then make my final recommendations. And I really hope that what you get is two messages. One is do everything you can do to prevent missing data and collect ancillary information about your key endpoints that will facilitate analysis strategies. So those are the takeaway bullets. So the problem is that the patients that are in palliative care or end of life with high levels of morbidity and mortality, and so we're going to have missing data for most of our important outcomes, and this will, if we totally ignore it, we will obtain highest estimates of change over time. We will underestimate usually the decline. And if you think about it, if you have a population and you're measuring something and all the sicker patients drop out, then the measurements actually look as they're stable over time, but in fact, in individuals, the outcomes are probably declining. So, in the text, it's very rare that survival is an important endpoint in any palliative care intervention. It's just not what we're about. But the focus actually is on, I'm going to refer generically to patient-reported outcomes, typically things like symptoms, activities of daily living, quality of life, and some other effort-dependent measures that maybe the patient doesn't say them verbally, but they have to be active within them, and something like a pulmonary function test or a 6-minute walk. I'm sure you could come up with a lot more. But those are usually what the focus of our palliative care interventions are trying to improve. and typically they have repeated assessments of those measures, and we're interested in either comparing the change over time or estimation of that change. We're really kind of conditioning on survival. We're looking at the quality of time prior to death rather than a more composite measure of both quantity and quality that we might be interested in if we were looking at, cancer therapies or, other therapies intended to prolong life. So getting into the missing data, and I'm going to try to be as more conceptual than formulas, but we just can't avoid this. So there's what we refer to as missing completely at random, and the definition is that the probability that an observation is missing is completely independent of what would have been observed if we could have observed it, and so it's totally unrelated to anything that's happening to the patient. And a good example might be an administrative stopping of the study. Also, covariate-dependent missingness. One good example is if the questionnaires aren't available in some languages, so you may have missingness in languages other than English and Spanish or something like that. And then we have the kind of the central definition that most methods actually rely on, and we call that missing at random. And so in this case, the missingness of the observations can depend on pre-observed data or covariates, but after adjusting for those, it's independent of what would have been observed if we could have observed it. Finally, we have missing not at random, and this is when the missingness does depend on the what we would have observed if we could have observed it, even after the adjustment. So most missingness due to morbidity or mortality fall into this category, and thus most of the, that'll be most of the missing data in palliative care studies. So this is the one we really need to pay attention to. And when we say non-ignorable, it means that basically we will get biased estimates if we ignore it. So into my teaching, anything we can do to prevent or mitigate missing data is obviously going to be desirable. And it includes things like educating staff and patients and caregivers to really understand the value of what we're collecting and why we're collecting it. There needs to also be a clear responsibility for obtaining assessments. If we kind of say we're going to get the assessment, we don't really say, okay, this person is the person responsible for getting the assessment. We're going to have complete data as we and developing a reminder system that may help whoever has that responsibility can be very helpful. In terms of the questionnaires, obviously keeping it short is desirable, though one of the hardest things to achieve. The other thing I would suggest is limit the length of the follow-up. Basically, if we have a group of patients where the expected survival is 30 days, collecting data on a very few patients at 6 months that data just is not going to be useful. And so, to think through, how long to do the assessments, be aware of the survival rates that you're expecting in your city. Allowing for multiple modes of collection is there's a lot of literature that suggests that there's minimal differences between collecting these type of assessments on paper versus electronically. So being flexible and being specific in your protocol about what is allowed, and maybe there's a preferred approach, but have specifics on if that doesn't work, what else can you do? What else is encouraged? And then I've been strongly recommending a for converting some of the users, and if somebody says, "Oh, I'm too tired" or something like that, have a backup plan of having a mini assessment, and to those people you say, well, could you do 3 questions or 5 questions? And you might get the answer be yes. Oh yeah, I can do 3 questions. And what we want to do is pick 3 questions that where there's a single question that is your point. So let's say depression was your primary endpoint. Just pick one question out of that questionnaire and think about that. And I'll talk a little bit about how you would use that in your analysis. But if you have one question that has a fairly high item correlation, something about what that ultimate score would be if you've been able to ask that. So think about that mini assessment as being a backup plan for getting some of your getting around some caregivers that are being overly protective of their ones or something like that. And then plan surrogate respondent. So something that we want to be assessing concurrently and after dropout. So the concurrent assessments might be this auxiliary data might be assessments by either a professional caregiver or by the family friend caregiver, or it might be if we're trying to get some measure of physical functioning, some like the ski or some other performance status measure that's assessed by the staff, might be explain a lot of the variation in the outcome that we would have seen. So the last two, particularly this one, is most important one, and you're rarely going to find a good data if you don't plan for it ahead of time. If you just go after finish the study and say, we have a problem. I wonder if we, collect data on something that we might be able to use. And in most cases, the answer is you didn't. But if you had thought about it ahead of time, you might have added in something to do that. So getting into the area of analysis, we avoid methods that assume missing completely at random. include things like complete case analyses, multivariate analysis of variance is one of those. Even univariate analyses, repeat these independent ones. Basically, if you analyze the data, do tests on the data at each time point separately, you're ignoring all the rest of the data that's been collected over time, and that makes the missing completely and you're basically analyzing a different patients at each time point, and it is subject to quite a bit of selection bias. One that I would strongly suggest you not employ are generalized estimating equations. And some people argue for them because they say, well, the outcomes we're measuring aren't nicely normal distributions, but it's actually the typical sample sizes we have in trials. It's not necessary for the distribution of the outcome to be normal. We're really the required theoretical thing is that the test statistic be normally distributed, and that happens with 30 or more subjects. So that's an argument against doing it because of the distributions. There are some strategies for adapting the GEEs to missing at random or missing not at random. They basically involved heavier weights on subjects that are like subjects that are missing information. But studies that we have where most of the missingness is due to morbidity, there really are observations on other patients that reflect the patients where we have missing data, and so there's really no observations to weight more heavily. So I would recommend against GEs in this setting. So this is an example where we're looking at the physical functioning as part of quality of life assessment. And what I have here is the upper lines are the estimates for those people who had all four assessments, or at least assessments through the fourth assessment. And then the next line, the ones had 3, 2, and then a single one. And this won't be atypical of some of the that you'll see where not only are kind of the general slopes associated with the length of time that they are on the study, but actually where they start off. So in this case, the patients with the lowest physical functioning were those that died the soonest, and the ones that had the highest values tended to be the ones that survived long enough to do all 4 assessments. Going back to what we were talking about, if we had done the complete case analysis, we would be analyzing only these subjects who are contributing data to that top line, and you can see how different that top line is from the other trajectories. If we were just doing those repeated univariate analyses, we'd be only analyzing those patients that had data at any one assessment. So recommended that you avoid those methods. So the probably the analysis strategy that you'll rely on the most are analysis strategies that assume missing at random, and they follow the likelihood-based methods offered generically to the mixed models. and use all available data. So any individual in the participant in the study who has even one assessment is included in the analysis. The assumptions is lacks two missing at random from missing completely at random, and they're easily reproducible, and there's basically software available in every language, the analysis package that you would ever use. So there is one choice that you will make when you choose these models, and one I referred to as a repeated measures model, and another is a growth curve approach. It depends on the duration of the intervention and the number of observations. So if you have a short duration trial and fewer observations, you're probably going to be using the repeated measures type of structure. If you long duration study and more observations, you're going to work on the growth curve type models, and when you have a lot of variation in the timing of the assessments, you're going to be it's difficult to classify the observations into a window of time that would correspond to the repeated measures. So you're going to do the curve. So if you want more details on that, again, that's when looking at my book will be really helpful, because I have some strong examples and show how to do those analyses. But one of the things that I want to add is conceptually, what does it mean to assume that observation is missing at random? And I saw this. This was the best explanation that helped me understand what was going on in the analysis, and how the estimates that I would get would with assumptions. And so this is a little bit of algebra, but if we based on the model that we fit, if we get this value for a certain observation on the ice subject, then it'll follow this formula, which translates into this. Don't worry about it. If you go back, you can look at it. But if you rearrange all of this, it turns out that the weighted average of the predicted values from all the other subjects that have observed data in the analysis, that's the XI data, and previously observed data on a particular subject. And when there is high correlation between the observations, a lot between subject variation, these previous observed data will dominate that kind of estimation, and when a correlation is lower, then the sticks with data will dominate it. So in the context of a care study, these would be the patients that are still surviving, or who are not experiencing enough morbidity to not be doing the assessments. So, and here, let me go to this figure. So these are the same plots that we had before. The solid lines are what we've observed, and these dashed lines in this study are what would be predicted and actually used in the estimation procedure, like an EM algorithm, for the missing assessments. And then what you can see is that I think the correlation was closer to about 0.5, and so that a 50-50 combination of the previous that's influencing this trajectory and what's happening in the patients who are still being observed. And so the curves flatten out, and we actually know from clinical observation that these trajectories tend to continue downward. So in this setting of this study that I'm showing you data from, we know that we have a lot of missing not at random data, and by doing analysis solely using we are going to get biased estimates. So again, if we're using the missing at random, what does this mean in our typical study? Well, we're going to tend to, when we're going to estimate change over time within a group, we're generally going to underestimate the decline that we would see. However, when contrasting these estimates between groups, particularly if those groups are determined by randomization, the bias may cancel out if there are similar dropouts in both groups. And it's this concern that leads us to, while we do our primary analysis using these maximum likelihood techniques, there's always a strong recommendation for sensitivity analyses. So what are our options for doing these sensitivity analyses? So we could do some multiple imputation with surrogate or ancillary data. We could do joint estimation with ancillary data, or something like the time to death or dropout. We could look at mixture models. And one thing that's common to all of these methods is that they really are attempting to convert the problem to being conditionally missing at random. So now we not only have the previously observed data on a particular subject, but we are conditioning on either these surrogate or ancillary data, or the time to death or dropout. Or with the mixture models, we're assuming that within each pattern, the data is missing at random. So I'll talk about that. I'll talk about each specific one now. So in the missing values, mutation is just definitely not recommended. It has multiple problems, including underestimation of the variance, and so the test statistics are all wrong. There are some that are still used, but they're becoming much less commonly presented. So the alternative is doing multiple imputation, and there are a huge number of options for doing multiple imputation. They include things like the MCMC, which assumes everything's multivariate normal. There's procedures for monotone dropout, which have actually recently been laxed to allow for procedures that aren't quite so restricted. Techniques, there's something called nearest neighbor and predicted mean matching. I like the nearest neighbor and predicted mean matching the best out of all of these, but that's a whole webinar on itself, which multiple imputation model. But so all of the techniques essentially assume missing at random and and generally result in the same result as max likelihood if you just use all available data or the data that you would have used in that analysis. So the critical issue is if multiple imputation is going to work in this setting, we need that exact data to convert it to continually missing at random, given this point is in surrogate assessments. Those assessments may be one source of that ancillary information, or a surrogate assessment like caregiver observations. And it's actually important that we have concurrent assessment where the patient can do the assessments. We directly substitute the caregiver data for the patient data. What we do is we develop a model that models how the patient is associated with the caregiver information or whatever our ancillary information is, and use that model then to predict what would have been happening for the patient, conditional on what the caregiver or that surrogate data is telling us. So that's the principle underlying a good multiple imputation in this setting. So again, the message is if you don't have that surrogate assessment, you're not going to be able to, really do anything that's better than the maximum likelihood estimation. What it requires fairly large data sets. It's not going to work so very well on studies with 30 subjects, but it'll work fine with 100 or more. 200, 300 will be great. And they need some good predictors. There has to be something that is that does explain the variation in the patient reports. And if it only explains 5% of the variation of the patient reports, it's not going to be very useful. Without that ancillary information, it's just a lot of work to do multiple imputation. So you need to think that through. So next set of models that I mentioned are joint estimation with and this one is with time to drop out. And so the concept is that patients whose scores decrease more rapidly are more likely to drop out or experiencing death. So we have a longitudinally measured outcome, and in this case what I'm showing is a mixed effects model, and you can see that this is the overall average, and then subjects, these dashed lines, will by this random effect, that these DIs. So there may be random differences in the intercepts and in the slopes between patients. And what we assume in this model is that those random effects are correlated with some function of either survival or dropout. In this case, I've used a log function, but there's a huge number of possible models, but that's appropriate. These models are also referred to as shared parameter models, and its value, that's the shared parameters. So basically the solution is now we've converted it to missing at random, conditional on the observed data and this survival or dropout time. The other way to use joint estimation models is to do the joint estimation with the surrogate or the mini assessment data. And again, we need the concurrent data over some time periods, and then may have follow-up using the caregiver or these mini assessments. And basically, we have a model that has these outcomes measured by the patient, and these are the data measured by the caregiver, and we allow them to be correlated, and that allows us to now assume that we're missing at random conditional on both the observed patient data and the observed caregiver data. So it reverses the assumption. Again, we've made it conditional on missing at random. So those are the two kind of general ideas about the joint models and how they would work. And there's lots of details if you're going to take that approach. Again, I could do a whole hour talk on just those. And then finally, I want to talk about pattern mixture models, which are, at least in this setting, probably my least favorite technique. They're very popular with some people, but I have been able to apply them well in any setting that I've been challenged to do it in. But so the idea is that we stratify the participants by the missing data pattern. We model within each strata. So within each strata, we're assuming that the data is missing at random, which is totally a valid assumption. Then we weight the betas from each of those stratas by the proportion in each one of the strata. So what the challenge is, well, there's often a large number of patterns. So if we have 4 assessments, we can actually have 16 different unique patterns. But actually, much more critically, is that we have what we call under-identified models that we can't estimate all of the parameters in the model that we need to, and so we have nothing to weight. And unless we do something like do some extrapolations or place restrictions on the parameters. So this is another example of the this, and in this case, we simplified the number of patterns by assuming that the missing data is random, and so we stratified by the timing of the last assessment, and that's reasonable because our assumption now is that the missing data are missing random within each pattern, and that's in setting probably valid. But the problem is that those are under-identified. So it's fine for those people who had all of the assessments, but those that had 3, 2, or 1, we can only estimate an intercept for this, or the first assessment here. Even if we were simplifying it to in slope, we couldn't get the slopes for this set of objects. This particular data set is maybe not unreasonable to assume that we could use an intercept slope model and get most of them, but about 25% of this sample only has a baseline, so that's really limit our assessments. But really hard to specify how you're going to do that extrapolation. This is another trial, and while that other trial, the first trial looked really nice, like you could argue for intercepts and slopes. In this case, we definitely have very non-linear trajectories, and it's really hard to figure it. And a lot of times you just don't know what this look like when you're writing the analysis plan. You don't know what it looks like until you look at the data. And to devise a plan after you've looked at the data is definitely not kosher. So this is why this is not very popular with me. There is one exception that I find useful, and it's when you have a pre-post design and you actually have the data on everybody at the pre, and you're missing the only missing data you have is at the follow-up, and so basically you're missing this. And I'm going to go through this. I'm not going to go through the details, but again, if you want the details, I can let me know, and I'll send you that chapter of the book. One of the possible restrictions is that we assume that dropout depends solely on the pre-data, and that would be the missing at random essence. And to do that, we basically regress the data on the pre-data, and we can only do that in the people that have complete data, this pattern 1. If we do a lot of algebra, we actually get this particular formula for estimating what mean would be at post data. And there's actually also an estimator for the variance for that data. The other, if we flip it around and we assume that the dropout depends completely on the post data, we use the same subset of patients and we regress Y1 on Y2, and even more flipping around of the data to get these predicted values at time 2 for the that doesn't have missing data, and the estimator can look like that. And then Bill actually made a really interesting observation, and he said that if we actually take this formula and this lambda equals 0, we get what we the assumption for the missing at random. It was to that first formula, and if we make lambda infinity, it is to this formula. And then he talked about doing the sensitivity analysis, because, well, it's rare in any one setting that it's all missing at random or all missing not at random. So what if we look across the values of lambda and see how it chooses the analysis? And so here's an example where I just look at the baseline in the 12-week data, and so this is the baseline where I have complete data for all settings, and this is my estimated mean at 12 weeks. And if I assume that it's missing random, I get an estimate of about 62. If I assume that it's dependent on the value missing not at random, I get this value, and different values I get things in between. So you can see that the change definitely, as we more dependence on the post-data, if the slope becomes a lot steeper, it actually changes a whole lot. And so it says in this setting that there's a lot of sensitivity of that within group difference to the assumption about the missing data. The good news is that when we look at the difference between those two posts in the two interventions, there isn't much difference, a little bit of difference, but they all remain non-significant, so that sensitivity analysis, our conclusions about between group differences doesn't change. So that's the one pattern mixture that I have good applications to. The use of pattern mixture models is it avoids the parametric specification of the dropout mechanism. It's easy to see what is happening by plotting results in each pattern, but the advantages are if we want to do formal comparisons of different groups, we have to make some restrictions and extrapolations, which require very strong untestable assumptions. And it's just so hard to plan what you're going to need to do or what would seem reasonable before you see the data. Okay. Some other strategies that they might, okay, I'm going to be done in about 2 minutes, that you might consider are looking at trajectories prior to death. So basically I'm plotting data where 0 is the time of death and going backwards, and this is dividing it by age, and you can see that there's a slight difference between the two trajectories. Mostly what you see is that there is a somewhat steady decline in approximately 1 month prior to death. The decline becomes somewhat steeper, and these differences due to gender, and I wouldn't make much out of this difference. I suspect the confidence intervals show that that's different. This is another thing where we've used splines, and they're a little bit harder to interpret, I think, than the slice linear that I show there. But this is performance status, and again we see a sharp drop fairly before, and it's somewhat increasing, very much similar to the previous. This is a McGill overall quality of life, and there really isn't much change over time. There's a little bit of wobbling, but not much change over time. So the thing is prior to death don't really do much for comparison of treatments, but they are interesting, descriptive, and may help us understand what's likely to happen. So recommendations are working on strategies to prevent and minimize missing data, and if I haven't made it clear, to prospectively collect that ancillary information for the important measures, your important outcomes. So thank you very much, and any questions, I'm going to turn it over to Sarah.
Thank you so much, Diane. Thank you, everybody, for joining, too. If you have questions, we invite you to use the chat feature in the lower right-hand corner of your screen. While we're waiting for those, I would like to just remind people to complete the evaluation that will be going out over email. And the slides from this presentation will be posted to the PCRC website, which is the link on your screen. And we also invite you to go to the PCRC website to look up details for all of our future webinars, including next month we'll be hosting Dr. Yael Schenker doing Team Science and Palliative Care. So we'll give questions. If things come up after the webinar, you're welcome to email me and I can forward them on to Diane. Diane, if some of our investigators don't have statistical teams that are able to help them with some of this missing data, the calculations, this be something that they can contact the DISC for?
Yeah.
The DISC, for those of you who may not have know about that, on our website, the Data Informatics and Statistics Core, there's a web page on the website for that, and you're welcome to email your question. You'll likely will hear back within just a couple of days.
There's opportunities when you're designing your study. It's possible to ask us to review, and you know, as you submit concepts, you know there will be a review. But if you're specifically concerned about the missing data strategies, you know, ask for an early missing data. Well, when you're originally designing your study, and for the pilot studies, we're encouraging people to call with one of the members of the DISC about their funded study to make sure that, you know, thought through some of the issues. So those are really good times to do it. And then, you know, if when you get to the analysis phase, your statistician do need to get more details, that time to contact them. But earlier is always better.
Yep.
Okay, now hopefully there's been some typing of questions.
We don't have any questions, Dan. I think that you covered everything. But if anything does come up, you're welcome to email Diane or the DISC through the website, or me, Sarah Garrigues. So thank you so much, Diane, for educating us about handling missing data, and we hope everybody has a wonderful rest of your Friday and good weekend ahead.